Hello friends, and welcome to the open course on diffusion in multi-component solids. This is the 12th lecture in this series, and in this lecture I will explain the concept of diffusion flux and various frames of reference used to measure the diffusion fluxes. Diffusion flux is a very important quantity in the analysis of diffusion. So, today we will talk about this concept of diffusion flux and the various frames of reference that we need for the measurement of diffusion flux. So, diffusion flux is defined as the amount of a component that crosses unit cross sectional area of a plane per unit time. Okay. Diffusion flux across the plane defined as the diffusion flux is usually denoted by the symbol J, and as you can see from the definition, the unit of diffusion flux will be amount of the component per unit area per unit time. So, if you talk about diffusion flux of component I, so its unit will be amount of I per unit area per unit time. Now, amount of I can be expressed in various units, that can be in terms of number of moles or number of atoms or weight, or it can be even volume. So, the various units of flux can be number of moles per meter square per second, or number of atoms per meter square per second, or kg per meter square per second, or it can be even meter cube per meter square per second. So, let us try to understand physically the quantity flux. So, let us consider a certain plane P at which we need to determine the flux, and our frame of reference is fixed at some physical plane in the laboratory fixed frame. Okay. So, our measurements are with respect to this fixed plane, this is called laboratory fixed frame, and we are seeing how much of amount of component I is crossing this plane P per unit time. Let us say the cross sectional area of the plane is A. Suppose we are considering a composition, we are considering a compositional front, let us call this composition Ci, as it sweeps through a distance dx across the plane P. So, this is distance dx, so this is dx by 2, this is dx by 2 in small interval of time dt. So, this forms a small volume element around P right, and if there are ni number of atoms in this compositional front, ni number of atoms of I, then the concentration of I in this small volume element we can write as number of atoms of I ni divided by the volume. Volume will be cross sectional area times dx. And by definition, what will be the flux? Because ni number of atoms have crossed plane P in time dt. So, the flux of I, and we are determining this with respect to a laboratory fixed frame. So, it is usually denoted as, the flux is denoted by a symbol tilde on top of J. This is called tilde, Ji tilde. It is also referred to as interdiffusion flux. Ji tilde is equal to number of atoms Ni crossing per unit area. So, A per unit time dt. If we multiply and divide by dx, we get Ni times A dx by dt. Now, we see Ni by A dx is nothing but the concentration Ci, and dx by dt, as dt tends to 0, is the velocity of this compositional front. Right. Let us denote this by ui. So, Ji tilde is simply Ci times ui. So, this is the expression that we get for the interdiffusion flux, that is the flux with respect to a laboratory fixed frame, which is the product of concentration of I and ui. It is also referred to as the mean velocity of atoms of I. Now, suppose if plane P was also moving, in this case we are considering plane P is stationary with respect to our lab fixed frame, but what if the plane P is moving? Would the flux still be same? No, right. So, consider an analogy. For example, you are standing on the median of a road, and then your job is to count the number of vehicles crossing you on one side of the road, right. So, suppose initially you are stationary and all the vehicles are moving, let us say, with some constant average velocity, right. So, you will see in certain amount of time certain number of vehicles will cross you. Now, suppose instead of being stationary, if you were also moving in the same direction of vehicles, now would the number be same? Will it be higher or lower? Because you are moving in the same direction as the vehicles, the number will be lower. The number of vehicles crossing you now will be lower, because you are moving with certain velocity in the same direction. If you are moving in the opposite direction, the number would be higher, because more number of vehicles now will cross you per unit time, right. So, similarly, if the plane P is moving in the same direction as this composition front, then the flux seen by plane P will be lower. So, if we express Ji with the frame of reference which is fixed to plane P, let us call it Ji phi, where phi is the velocity of plane P. Then in the new coordinate system, the effective velocity will be ui minus phi. Right. So, this is basically Ci times ui Ci times phi. So, we can write Ji phi is equal to Ji tilde minus Ci phi. So, this shows us that the value of flux will depend upon the frame of reference that we are choosing, and the fluxes from one frame of reference can be converted into fluxes in another frame of reference best if we know the velocity of the frame of reference. Okay. So, what are different frames of reference that we use? So, let us talk about the frames of reference used for determining the interdiffusion fluxes. So, let us now talk about frames of reference which are typically used for measuring the diffusion fluxes. So, the first one is called volume fixed frame. So, volume fixed frame is basically fixed on local center of volume of all components such that the net flux expressed in terms of volume is 0. So, let us try to understand this a little more. What is the volume fixed frame? So, suppose partial molar volume varies with composition. We consider the diffusion between two elements, let us say A and B. Let us say they are completely miscible into each other. So, what happens? As some A atoms move from left to right and some B atoms move from right to left. So, the net flux of A will be from left to right, B will be from right to left. So, consider when initially only one atom of A jumps from left to right and one atom of B jumps from right to left. Although in terms of atom there is only one atom exchange, but in terms of volume it will be different, right, because A will have different partial molar volume than B, and suppose V A bar is greater than V B bar, then after some time, since there is a accumulation of A on right side, accumulation of B on left side and depletion of A on left and depletion of B on right. So, in effect there will be increase in volume on the right side. So, the center of volume has moved towards the right because A is having higher partial molar volume than B. Now, if we fix the frame of reference along the local center of volume, then the net flux in terms of volume or the net volume movement across that plane will be 0, and that is our volume fixed frame. So, typically we express flux in terms of number of moles of I per meter square per second, right. It can be Ji tilde or it can be Ji. Let us call this Ji V. That is the flux in volume fixed frame of reference. Now, the net flux expressed in terms of volume is 0. So, if we need to convert this moles of I into meter cube of I, what do we need to do? Multiply by meter cube of I divide by mole of I, which is basically the multiplication by partial molar volume. So, we know the sigma Vi bar Ji V should be equal to 0, and that is again the significance here. So, in terms of volume fixed frame, again there are only n minus 1 independent fluxes, the nth one will be dependent because there is a constraint. Okay. So, now from the equation that we derived, we can write J I tilde or J I V, you can write J I V as J I tilde, where J I tilde is the interdiffusion flux or flux with respect to stationary frame of reference, minus C I times u v, where u v is the velocity of volume fixed frame. This volume fixed frame is generally denoted as R superfix V, RV. So, if we multiply both sides by molar volume and then take the summation over all components, we get sigma V I bar J I V equal to sigma V I bar J I tilde minus u v will be same for all components. So, u v times C I V I bar, and we know the left hand side is 0 because of the constraint put by the volume fixed frame. So, we get sigma V I bar J I tilde minus, and sigma C I V I bar we have seen what is it? C I V I bar is basically the volume fraction, the summation of volume fractions is 1 minus u v. So, u v is equal to V I bar J I tilde. So, you will notice that sigma V I bar J I tilde is not 0, where J I tilde is the stationary the diffusion flux with respect to stationary frame of reference. Okay, but if we use volume fixed frame, we have this constraint. Now, this u v is an important quantity, and u v in fact varies with distance and with time. It will not be same as we go from left to right. So, it varies with x as well as t. So, u v is a function of x and t. So, this is the volume fixed frame. Similarly, there are other frames of reference. So, the second one is mass fixed frame. Mass fixed frame is fixed on local center of mass of all components such that net flux so obviously just we can give the similar analogy as volume fixed frame, right. The molar mass of each component is not same, or atomic mass of each component is not same. So, the mass local center of mass will shift towards or shift in the direction of diffusion of heavier element, right, in case of that binary diffusion. So, if we stick our frame of reference to that local center of mass, then obviously the net mass movement will be 0. So, if we consider J I m, that is the flux expressed in terms of mass fixed frame, to convert it to in terms of mass, what do we do? Multiply by kg, divide by mole of I, kg of I per mole of I is basically the molar mass, mi bar. The net flux in terms of mass is 0. So, this is the constraint put by the mass fixed frame of reference. So, if we apply this, we express JIM in terms of JI tilde, it should be JI tilde minus CI UM, where UM is the velocity of our mass fixed frame. If we multiply by molar mass and take the summation, mi bar JIM should be equal to sigma mi bar JI tilde minus UM times sigma CI mi bar. What is CI mi bar? Here is mole of I per meter cube of alloy times kg of I per mole of I. So, this is basically kg of I per meter cube of alloy, right, and so the summation will be kg per meter cube of alloy, which is the density. So, this should be sigma mi bar J tilde minus um times rho, rho is the density, and so the expression for will be sigma mi bar J tilde divided by rho. We can also fix the frame of reference with respect to local center of number of moles, and that is called as mole fixed frame. It is fixed on number of local center of number of moles of all components such that net flux expressed in terms of so we typically express flux in terms of number of moles. So, J you can write J I n is equal to 0, sigma J I n is equal to 0. So, J I n denotes the diffusion flux of I with respect to the mole fixed frame of reference. So, this we know J I n is equal to J I tilde minus C I U n. Where un is the velocity of number fixed frame, and if we take the summation, we will get sigma J I tilde is equal to un times sigma Ci. What is sigma Ci? Number of moles of alloy divided by meter cube of alloy, which is nothing but inverse of molar volume of the alloy, right. So, un or the velocity of mole fixed frame is basically molar volume times sigma J I tilde. So, remember these expressions all we are deriving assuming we are expressing the flux in terms of moles per meter square per second or moles per area per unit time. Okay. So, our inherent assumption is typically we express fluxes in terms of moles per unit area per unit time. So, the advantage of using these different frames of reference is that we can make one flux dependent. So, we will see that later on that it will help us to reduce the number of diffusion coefficients needed to describe the diffusion in a particular n component system. There can be also another frame of reference which is fixed to a particular lattice plane, and that is referred to as lattice fixed frame of reference, or it is also referred to as Kirkendall frame of reference. We will talk in depth about that sometime later. Okay. So, any question so far? All right. So, we will stop here.